Welcome, and thank you for joining us. My name is Dane Lee, and I'm Professor of Physics at the Facility for Rare Isotope Beams, or FRIB. Today's public talk is part of an initiative at FRIB called the Advanced Studies Gateway. The goal of the Advanced Studies Gateway is to inspire people. We bring together researchers, innovators, creative thinkers, artists, and performers from all fields, and strengthen ties between Michigan State University and the community. Today we have the great pleasure of presenting a public lecture by Sophia Economou from Virginia Tech University entitled Quantum Computing Stack, From Control to Algorithms and Back. Professor Economou is a professor of physics and T. Marshall Hahn Chair in Physics at Virginia Tech. She is the founding and current director of the Virginia Tech Center for Quantum Information Science and Engineering. She was elected American Physical Society Fellow in 2023 and is the first recipient of the Jacob A. Lutz Award for Eminent Scholars in the category of Science, Engineering, and Technology at Virginia Tech. Her research focuses on theoretical aspects of quantum information science, including quantum computing, quantum communications, and quantum simulation algorithms. If you have any questions during this talk, please type them into the chat or the question and answer dialog box. At this time, it is my great pleasure to introduce Professor Economou.
Thank you, Dean. Thanks a lot for the invitation and the opportunity to present my research and what I found exciting. So let me share my screen and let me know if my slides show okay, please.
Yeah.
Can you see the slides all right?
Mm-hmm.
Thank you. And I'm also going to try to use my laser pointer. Great. So today I'll talk about quantum computing stack. I'll explain what I mean by this and why we're actually not at the place to abstract to full stack, and how I view current research in the field as spanning the whole stack, all the way from the bottom to the top. So quantum computing has its origins in quantum mechanics, which is the theory that describes, explains the physics of electrons, atoms, molecules. We usually say it's the very small. Recently, there was a Nobel Prize in Physics, which also showed, highlighted research that shows that you can have quantum effects at a more macroscopic scale. Early experiments is what prompted scientists in the 20th century to come up with the theory of quantum mechanics. And that's because many experiments, physics experiments people were observing could not be explained with the formalism they had set up. For example, Newtonian physics that they could use to explain things like planetary motion. And examples of things people saw that they could not explain with classical physics is things like atoms emitting light at specific frequencies and not at a continuum. A well-known experiment in physics called the double slit experiment that showed that electrons, instead of just being point particles with well-defined position and velocity, can behave like waves. And there's many more. So I know that Steve Gervin gave a very nice talk in this series about a month ago. So for more background on the experiments that prompted the development of quantum physics, I strongly suggest that very nice public talk. Let me just focus on a particular example that'll be very relevant for the rest of the talk. Let's look at atoms. So atoms have discrete energy levels. They cannot have energies that span any value. So this is an example from the hydrogen atom. We have particular energies that are allowed, and the electrons, instead of being point particles, like I said, are described as a sort of density that you can think of as a probability distribution. It's a little bit more subtle than that. But each energy level has a particular wave function, as it's called, which tells you how this charge is distributed in space, or you can think of it, what is the probability to find the electron in a particular place in 3D space. Things are more subtle than that. In addition to this energy quantum number. Oh, sorry, before I get to that, let me just point out that this finite set of frequencies of the emitted light, you can understand it because the energies are discrete. When the electron drops from one energy level to another, it emits light to conserve energy, and therefore that light also has discrete frequencies. So let me get to another more subtle point. There's an additional intrinsic property that we call the spin. And that means that each of these states, in addition to having a spatial distribution, like you see here, they also have this intrinsic quantity that we usually say it can be up or down. I'll come back to that, so I thought it's important to show it early on. Now, quantum already has applications in technology. This is sometimes forgotten in our effort to build quantum computers and with all the hype around this field. But there are plenty of examples where quantum mechanics is needed to understand and build technologies. For example, the laser relies on this discrete energy levels of atoms and some collective phenomena that can happen. We have superconductors, which need quantum theory to explain their physics, and superconductors can be used as detectors. There's a nice talk by Katya Novak under the series where she talked about her group superconductivity experiments, and you can find out more about this there. And then we have things like atomic clocks, etc. So in all these technologies that already exist, there's clear quantumness, but we're still not exploiting the full features of quantum mechanics. And that's what I'll talk about today. Sometimes people call this quantum 2.0 or the second quantum revolution. And the three fields or subfields of quantum technologies are quantum computing, perhaps the most celebrated, quantum communications and quantum networks, as well as quantum sensing. Today, I'll focus mostly on quantum computing, but many of the concepts I'll introduce also pertain to the others. So these technologies make much more strong use of quantum mechanical features. Hopefully, it'll become clear to the audience what I mean by that very soon. It's important to note that the required level of control to build these technologies is truly unprecedented. So we need to control quantum systems with such precision. And these quantum systems are so fragile. And that's, of course, the reason that we don't have these technologies yet and that it's so difficult to build them. And the building blocks are quantum bits, which let me try to explain in a moment by first talking about classical bits. So classical bits, I think everybody's familiar with, are abstracted objects that can take two values and with which we can build logic and do computation. So it's kind of nice to think about a manifestly binary object from our everyday life, which is a coin. So a coin, as we all know, can either be heads or tails, and it can be nothing else. And if it's heads, it cannot be tails. If it's tails, it cannot be heads. This is kind of obvious, but it's important to stress it because if I have a quantum bit, I can think of it as a coin that has this peculiar property of being in a superposition of heads and tails. Of course, we don't see this with actual coins, but we see it with quantum systems. But it's to some extent, it's as strange, as this implies. At least it was for the physicists who discovered that this is how nature behaves. Sometimes you hear people saying that a quantum system can be in both a head and tails or both 0 and 1 at the same time. This is somewhat of a sloppy language, but it conveys this point of superposition. And another important thing about quantum systems that differentiates them from classical is that the way measurement behaves. So if I make a measurement, I will see either heads or tails, and the probability to see each depends on these coefficients over here. So that means that these coefficients have to satisfy the property that the absolute square sum is equal to 1, since these are probabilities. Okay, so this is one feature. Another stranger feature is the concept of entanglement, which is extremely important for the technologies I mentioned. So let's consider, again, 2 bits or 2 coins. So if I have 2 bits or 2 coins, they can have 4 distinct values. And again, if the 2 coins are both heads, then they're definitely not heads, tails, tails, heads, or tails, tails. Quantum mechanically, 2 qubits can exhibit a superposition of these 2 qubit states. So as I wrote before, a superposition for a single qubit, I can have a very similar thing, but now for 2 qubits. And you see that I have all these 4 possible states appearing in the superposition. And for some choice of these coefficients, I can have what we call maximally entangled state. Let me show you an example. Consider this state where the 2 qubits are in a superposition, equal superposition in this case, of heads and tails. This has far-reaching implications, and it also gives rise to experiments that were hard for some physicists to accept, even Einstein in the early days of quantum mechanics. So consider this experiment. I have a state like this, and I take qubit 1 and I send it to the US, and I take qubit 2 and I send it somewhere to Europe. And I'm denoting these wavy lines here. I'm trying to denote entanglement. So don't think about this as a physical interaction. This just reminds us that the state we have is this one over here. So this is just a different representation of the state where I'm trying to spatially show spatial separation of the 2 qubits. And one thing you'll notice here is that this is a very kind of smudged coin over here. You cannot tell if it's heads or tails. And that's very intentional because each qubit does not have a well-defined value. So if I make a measurement, let's say I measure qubit 1 over here, I'm going to have a totally probabilistic outcome of 50% heads, 50% tails. But what's remarkable is that once I make that measurement, the other qubit will agree 100% of the time. So even though each qubit does not have a well-defined value, it doesn't have well-defined properties in some sense, collectively they do. And there's this correlation that persists and that we don't see classically. This is a really quintessentially quantum mechanical effect that allows us to come up with ideas for technologies. For example, I can do something called quantum teleportation if I have a state like this, where I can teleport the state of qubit 1 with this, to Europe by making a measurement in a lab in the US. I could, in principle, teleport a state of another qubit over here by consuming this entanglement. And entanglement is important not only, that gives rise in turn to applications in cryptography, the possibility of implementing quantum networks where information can be securely transmitted. But teleportation is actually also important in quantum computing, where you can teleport information between different parts of a quantum computer. Another feature of entanglement, and this is very important for the rest of the talk, is that whereas a single qubit can be specified by 2 numbers, and therefore we need only linear number of coefficients here to describe a state of independent qubits, shown over here. So you see here, every qubit has its own superposition. So if I were to make a measurement on qubit 1, that would not depend or affect a measurement on qubit 2, etc. So this is not a classical state in the sense that I still have superposition, but it's not the most general quantum state because it lacks entanglement. For a general state, which is an entangled state, I can have a superposition of any of the 2 to the n, so this is an exponential number now, coefficients, states that I have, and therefore coefficients. And that happens generically for most values of these C's. I'm going to have some entanglement in the state. And these properties allow us to cook up quantum algorithms. And there's several quantum algorithms that people have devised. Perhaps the most famous is Shor's factoring algorithm. And this is sort of what drove the field of quantum computing for many decades until it became a more popular and a field that now has also industry. But for a long time, the main application that people were pursuing, especially because governments are interested in this, is Shor's algorithm. And the reason is that this has important impacts on the crypto system we're using on the internet. So a lot of things like economic and national security would be impacted if someone had a quantum computer and could factor these large numbers. Another well-known algorithm is Grover's algorithm. This is more used as a subroutine in other quantum algorithms. And perhaps the most important application, at least from my point of view, and I think most of us who are interested in science, is the fact that you can use quantum computers to simulate other quantum systems. And in turn, what we can do is we can understand better chemistry of molecules, chemical reactions, material science, and physics, and that could have applications in various industries. So the distinction of quantum computers and classical computers is very similar to what I showed you before with the coins and the quantum coins. But of course, we also have, to physically create these things, right? So I showed you a very abstract representation using coins or bits, but all these things are implemented in a physical system. And our existing computers use transistors, and these can be made to behave as classical bits. In quantum computers, we replace these transistors with quantum systems that have superposition and can become entangled with each other. But again, I want to stress that it's very important to control this entanglement in a very precise way. Okay, so there's many different approaches to building a qubit, and the community is pursuing all of these and more. There's a lot of academic labs and now industry labs as well that are using superconducting qubits. I'll say a little bit more about that later in the talk. We can have spins. I showed you this property early on, that electrons can have this intrinsic property called the spin. And if you remember, that could take two values. So it's a very natural qubit to consider because it maps to this binary character of a qubit. And then we can also use, and people are exploring, atomic qubits, and as well as photons. And this is not an exhaustive list, by the way. So if there's clarification questions that I can answer, Dean, please let me know. I'm not monitoring the chat.
Okay, there are actually quite a few that have accumulated. So the first is, how is measurement made?
Yes, so it depends a lot on the system. Let me show you an example here. So let's take an atomic qubit. These are the energy levels I showed before. I discussed a little bit the hydrogen atom, where an electron can take energy values that are discrete, shown over here, and can be in these states that I showed in the early slide. And one thing we could do is we could select two of these levels, because I need two states to create a qubit. And I could say this is my qubit. Now I can control this with electromagnetic fields. So for example, a transition of this order would be driven with a laser. But there's actually more states over here because I have that spin number, and I could have microwave fields that drive it. A measurement could be done very similarly. So for example, what I could do is I could go to the state 2s, and drive a transition to one of these higher states, and then look at the light that comes out. And because I would only be driving this state in this example, I would be able to distinguish my 0 from my 1. This is one way to measure. There's many ways, and it's very, very system dependent. And even within a particular system, for example, an atom, there's different ways you can do it. I hope that at least partially answers the question.
There's one more question. Maybe I'll combine two of them together. It's how do we create entanglement? And the other question is, how do we physically split the two entangled qubits so far away?
Okay, great questions. So to create entanglement in the first place, I need some kind of physical interaction. So I need the systems to be close to each other or interact. Also very system dependent. For example, since we're focusing on an atomic qubit, and the reason I picked an atomic qubit is that I think it's conceptually the simplest qubit because, for example, hydrogen atom is just the proton and electron. It's probably the simplest non-trivial quantum system you can think of. So if I have atoms that have these energy levels, there exist some energy levels that are very far up in energy. And if I excite my system up to that level that I'm not even showing here because it has a very high quantum number, as we say, so very high energy, then states like this can have interactions with the corresponding states from another atom. And that's what people do in neutral atom quantum computers, like the ones developed at Harvard and QERA and other places, called the Rydberg. So these are very highly excited states that exhibit a certain type of interaction that allows to build an entangling gate out of it. In other systems, you might have other types of interactions, but across the board, you need the systems to come close together. And the second part of that question was, how do you physically separate them? Yes. So once you've brought them together and you create this entangled state, let's say the state I showed you, which was heads, heads, tails, tails, or 0, 0 plus 1, 1, then you can pull apart the systems in any way that you can move a qubit around. So this is a little bit subtle for systems that are pinned in place. For example, I'll show you later superconducting qubits. And those typically don't move their actual circuits. But for atoms, for example, people trap them with a potential. So you can actually use this trapping. It's called optical tweezers. And they can move these around and separate them physically. Another example, and what's actually used in quantum networks, is that let's go back to the atom that we like so much. So imagine that I have an atom in this state 1, and that decays to the 0 state and emits a photon. We can make things such that photon, so photons have a speed, right? They travel at the speed of light. So we can arrange things such as that photon is entangled with a system that emitted it. So that's a very natural way to separate them out, because you can think of the atom or whatever your qubit, your matter qubit, sitting in some lab, and then the photon being emitted. And what people are trying to do is pass them into optical fibers, and then they can travel the same way that light travels and gives us the internet. Of course, this is much more delicate because in this example, you just have one photon. Whereas when we have our classical signals to communicate with optical fibers, we usually, have a higher intensity light, and that light is also not sensitive to things like loss and measurement. Hopefully that addressed both questions.
Yeah.
Okay, great. So yeah, feel free to let me know if there's anything else I can answer as I go. Right, so I showed you an example of an atom. Neutral atoms have actually made great progress in a very short amount of time. You can see here a setup. Trapped ions is another type of atomic qubit, but it's charged. So even though these are both atoms, they do have a different type of operation. The way we trap them is different, etc. Superconducting qubits are circuits of superconductors, and they're explored by companies like Google and IBM. And then there's also spin qubits that I mentioned earlier. And again, this is not an exhaustive list, but it's meant to show you that people can now create these devices with tens to hundreds to thousands of physical qubits. This is still very far from what we need to do universal quantum computing, but there has been great progress over the last decade or so. And a fun thing for people who want to kind of get more hands-on experience is that some of these companies offer quantum processors available in the cloud. So people can go and do experiments, simple experiments with these. Here are some examples of qubit layouts. I mentioned superconducting qubits. Every circle here corresponds to a qubit, similar here every cross. And you can see here that the qubits interact with their neighbors. That's how we built the entangling gates and the entanglement we need. And ideally, you want to make these interactions switchable because you don't want your qubits to talk to each other unless you're trying to implement an entangling gate on purpose. So these are qubits that are kind of stuck in a lattice in space, as you see here. I mentioned atomic qubits already, and I also mentioned in response to a prior question that these can be moved physically around. So that's a nice capability that they bring to the table, because I can have more connectivities, and this is a reconfigurable architecture. So it gives a lot of opportunity of which qubits I can entangle with each other. You can have separate zones like storage and measurement, etc. Of course, there's also challenges with moving things around, because then you give them more opportunity for errors to happen. But yeah, this is all very much ongoing research. So there's a lot of qubits shown over here, and people have started to control a large number of qubits. I just want to highlight some recent experiments. IBM put a paper, I think this is from last week, where they created a very large entangled state. Sometimes we call this a cat state of around 120 qubits. There was a paper by Google that I think was also featured in the New York Times, where they did some many-body, they ran some many-body circuits and showed some correlations that the claims they cannot be simulated classically. And in this platform, there's been great progress toward quantum error correction, which requires formidable efforts, an unprecedented amount of control, and many physical qubits to get logical qubits. But what I kind of like about these three together is the different types of things people are trying. So we're not yet anywhere near to running an actual quantum algorithm like Shor with quantum corrected qubits, but we can still do fundamental research that we can learn a lot from it and also lead to applications. And we can also understand the device better by doing these experiments. So there's very diverse things we can do with many qubits, even at this stage. So that brings me kind of to this idea of a stack, which it's a nice way to think about it in an organizational way. But I also want to make the case that because quantum computing is very much under development, there's no real separation like I'm showing here. And actually, that's the point I'm trying to make, that there's a lot of fundamental research going up and down and making connections between these different parts. So here's the outline for the rest of my talk. I'll tell you a little bit about quantum algorithms and specifically quantum simulation, highlight some of the work coming out of my group on adaptive algorithms. And then I'll jump sort of down here where we look at the physical system, the qubit, and think about how can we control it in a way that we tame the noise, we tame the errors, and we create gates that are closer to what we need. And hopefully there'll be a natural connection that you can see going from this control level all the way back to algorithms. So I hope I make it there in the rest of the time I have. So let's start from applications and specifically quantum simulation. This is an idea that Feynman and others had introduced in the early 80s. And it is a very visionary statement, to make if you think about how many decades went since the early 80s to now, where we're kind of barely starting to do these things. So what do we mean by simulation? You can think of roughly two ways of separating what we mean by quantum simulation. One is analog. So I have a system, I know its equations, I know, what equations I need to solve for it. And a very important quantity here that features in the Schrödinger equation, which tells us how to describe quantum systems, is something called the Hamiltonian. You can think of this as corresponding to the energy of the system. It has in it all these energy levels and the states that I showed you. So having the Hamiltonian means that you know what equations to write down, but you still need to solve. So each system has its own Hamiltonian. We know how to write these down. So what we could do is we can take a simulator where we can control it pretty well in terms of the parameters and try to emulate this Hamiltonian onto the simulator. So this would be a specialized machine where I would try to recreate a particular physical system on another physical system that's more controlled. So it's not a general purpose machine. It's not a quantum computer, but it's an interesting approach for doing experiments to understand the physics of various systems, and people have done very nice work over the last several decades. On the other extreme, we have digital quantum simulation, which means that I can, in principle, do any simulation. Any quantum system can be simulated if I have a full operational quantum computer. But doing that is very hard. I need a very large overhead in terms of number of qubits, amount of control, etc. So the rest of my talk while it will focus on digital quantum simulation, there will be analog features coming in. And you can probably take away from this talk that there's a continuum between these two paradigms. So let's see some work people have done already in this. I'll be narrowing down the scope of what I'm going to talk about to simple systems like molecules. I say simple, but even larger molecules are not easy to simulate. And these were over the last decade or so. There was very interesting experiments by Google, IBM, IonQ, and others in industry and academic labs, where they took small molecules. When I say took, I mean took the Hamiltonian, the thing they needed to solve for a small molecule. So, for example, this is a hydrogen 2, lithium hydride, beryllium hydride, and solved for these curves, which is the energy of the system, the molecule, as a function of the distance between the atoms in the molecule. So these are things we can do on our everyday computers. They're small systems, so they don't suffer from this blowing up, exponential blowing up that I showed you earlier that quantum systems do. But it's still important experiments because they showed that we can, in principle, do this, right? They're not useful at this stage. They're very small systems. With our classical computers, we can go much higher and with better accuracy, essentially solving them exactly. But it's the first steps toward doing a non-trivial demonstration of quantum simulation. So let's see what's the simplest problem we can solve. And that's what the experiments I just showed you did. So let's say I have a molecule. This is more complicated than what we're trying to do at the moment. I mentioned that we have this object called the Hamiltonian. It is what enters the Schrödinger equation in order to solve for the energies and the states of the system. So the things that enter here is the kinetic energy and also the interactions, which are Coulomb interactions between electrons and the attraction between the electron and the nuclei. So this is the Schrödinger equation written down. It has a form of a so-called eigenvalue equation. If that doesn't mean anything to you, don't worry. I'm going to try to represent it in a way that's familiar based on what we discussed. So as I mentioned, quantum systems have discrete energy levels. So by solving this equation, we find the energies of these energy levels. So that's what these E's are. And we also find what the states are, which are these blobs I showed you early on for the hydrogen atom in this particular case. So we know how to write down the equations, that's H, but solving them is the difficult part, right? The hydrogen atom is very simple. It's a textbook problem. Every physicist has solved it at least once, and we get out these. For larger systems with many electrons, this becomes a difficult problem just because the space of states grows exponentially. So in quantum simulation, we're trying to take advantage of the fact that our quantum computers are quantum systems, so they have the right type of scaling, but we still have to decide how do we map something that's electrons to qubits, which are not are different in nature, and I'll try to explain in what way. So we have our equations for our molecule. We have our, and we're trying to figure out what to write down, how to express these on the quantum computer. Okay, first we make some approximations. Physicists always do that to make our life easier. And these are reasonable things we can assume. So one thing is that nuclei are heavy, so we can easily or justifiably keep them as static and just solve the electronic problem. That does not help us with scaling. We still have all the electrons to deal with and all the entangled states that can come out of these interactions. But another thing we can do is we can say, okay, let me solve a simple problem first. Let's say a single particle problem, which does not have this exponential scaling, and then form something we call a basis. And that's very similar to what I showed you before, these states that we had. So let's go back to our old friend, the hydrogen atom. We have the electron, just one electron. So this is the simple problem we can solve. And as I mentioned before, we have these possible states, and they also have this property called a spin. So here I have four spatial states, but each has spin up and down. So there's 8 total. And I'm just arbitrarily truncating to 8 states. There's nothing special about 8 states in this case, just to show you. And what we call the ground state, the lowest energy state, is the electron occupying one of these lowest energy states. Now, if I have multiple electrons, I have to be careful because electrons follow something called Pauli exclusion principle. And you can think of that as the electrons not liking each other and not wanting to be in the same orbital state. And that means that each orbital, each of these states I showed you in the previous, let me go back here. So each of these can either have one electron or be empty. It cannot have 2. So here's a state that is allowed out of these 8 orbitals. Let's assume my problem has 3 electrons, like I shown over here. I can put an electron on each of these 3, but you see that 2 electrons do not occupy the same state. So it's a nice feature of quantum mechanics that orbitals have this binary character because it's a very natural way to map to a qubit. And of course, this is a quantum state, so it can also be in a superposition. So the general state will kind of look like this. There's more states I didn't write down, but this is an example where I have 3 electrons and I'm distributing them over 8 possible states. And you see 2 electrons never sit on the same state. And the problem of solving the Schrödinger equation is actually figuring out what are these coefficients over here and finding the ground state energy. So how do we map to qubits? I already mentioned that I keep a set of orbitals. There's some intuition that enters here. How many do you keep? You cannot keep infinitely many because you have a finite storage. So let's say, I have my reasons to keep 8 of these. And we already said that each of them can be empty or occupied, meaning each of them in some sense corresponds to 0 or 1. So we can go and we can allocate 8 qubits out of our quantum processor and say that, for example, qubit 20 over here, I made an arbitrary choice, by the way, there's nothing special about this set of qubits. Qubit 20 over here corresponds, to the topmost orbital here. So if this one is occupied, I would call, that would be my state 1 in my qubit. If it's empty, that'll be my state 0, etc. It's a little bit more subtle to map the Hamiltonian itself. I just put this here for the physicists in the audience, but just to show you that you get a lot of terms. And that's kind of where things start to get hairy in how you do the quantum simulation. But let's say we also did this step, we know how to do it. What do we do next, right? All I've told you so far is that I solved the single particle problem. I know what these orbitals are. And my problem is now, how do I allocate electrons on them? But on the qubit side, what do I do? So let's go to classical algorithms. I have logical gates that create circuits. I have my input-output qubits, and I have things like AND, OR, XOR, etc. On the quantum side, I have quantum circuits. They look very similar in the sense that I have input, output qubits, and I have gates. These gates can take two forms: single qubit gates, cutting only one line here, or gates that connect two qubits. And I can form something that I call a universal gate set. That means I can form a finite collection of gates that I can combine to approximate any circuit. And that's how we envision doing universal quantum computing. However, at least in the near term, we can remember that instead of having coins and zeros and ones only, we have superpositions. And these superpositions can be arbitrary, right? A and B can take a continuum of values, which means that the gates themselves take a continuum of values. So classically, I can have a NOT gate, I can turn 0 into 1, but in quantum, with qubits, I can also go sort of halfway or a quarter or even at infinitesimally small rotations or going from one to the other. This gives me an opportunity to create parametrized quantum circuits. So if you see here, I can create circuits that have parameters in them, and then I can set up optimization problems. So I can tune these parameters, make some measurement over here, and set up an objective function once I have mapped my problem. So why is this interesting? It's interesting because there's something called the variational method in quantum mechanics that I can phrase as an optimization problem. So I can write down a trial state for my quantum system that carries some parameters. And I'm guaranteed by quantum mechanics that if I measure the Hamiltonian of the problem I'm trying to solve, I'm guaranteed to not go below the ground state energy. So there is this method that allows me to kind of tinker around with the parameters in the circuit in an effort to find the ground state, for example, of a molecule. And we can go around in a circle, and that's what people do with the variational quantum eigensolver. So this is an example of a more near-term algorithm where I'm using my quantum computer together with my classical computer. And I use the quantum computer what it's good at, which is to prepare quantum states. So I can deal with the scaling problem. And I make measurements on it. I feed my measurement outcomes to the classical computer. And I go around and I try to minimize that quantity. So an important question here is, how do I choose the circuit, this parameterized circuit? There's no prescription in how to choose it. And people have done various things. I'm not gonna go into great detail, but all I want to say is that there's a lot of freedom in choosing the circuit. And there's also a lot of wrong choices you can make. So for example, you can choose gates that are natural to your system, but these suffer from optimization issues. You can use more things inspired from chemistry or physics, but those can lead also to problems like long circuits. And you don't want to have long circuits because, as I mentioned, quantum systems are very fragile. There's a lot of errors in them, and we're not at the point where we can perform quantum error correction. So we are trying to keep our circuits shallow, like you see on the right, and not have too many of these 2-qubit gates that cut across different qubits, because these tend to be more erroneous. So here's an example where the right is better than the left. And let me quickly tell you how we're trying to solve this problem. So we have introduced an algorithm that is adaptive, and it uses the quantum computer to tell us how to construct our circuit. So we take the stance that quantum resources are precious. We don't want our circuits to be too deep. We don't want to have too many of these gates that cause errors. So we're asking the quantum computer with every measurement, is this a good choice or not? And the gates that are a good choice, we add them to our circuit, and then we do optimization. So the idea, the take-home message here is that we grow our quantum circuit dynamically, and this way we problem tailor this trial state, because we get input from the quantum computer based on the system we're trying to simulate. I'm going to skip too many details on this, but I just want to show you that this algorithm performs better than competing ones, in the sense that it lowers the energy more. So this is the error in the energy as a function of the interatomic distance, and you want to be as low here as possible. And you can do this with fewer variational parameters compared to this competing approach, which is the orange line. So I don't want to make this talk too technical, but I just want to show you that doing this adaptive trick allows you to do much better on both fronts. You get a better answer, and you don't use as many quantum resources. My group has done great work on this in the recent years. So I want to just, leave the slide up to show you the recent progress. I definitely, this is not the talk to go into details, but I'm happy to answer questions if there are any. Now, one thing we've been assuming so far is that I can change my parameters, and in some cases change them infinitesimally, with infinitesimally small steps, very small steps, to create circuits like this. But what do these gates really mean, right? Each of these gates can be implemented in many ways, and they're implemented by using electromagnetic pulses. I showed you an example early on with a laser driving an atom qubit. And the things I can change is the pulse shape, the amplitude, the frequency, etc. So let me go down to the bottom of the stack and tell you about, in the last several minutes I have left, about the Schrödinger equation, and the fact that the most general Schrödinger equation is not what I showed you before, right? We've been talking about this equation over here, where you can, try to solve it to find the energies and the states. But the more general equation is actually time dependent. And this is what we're doing on our qubits. We're evolving them with time dependent Hamiltonians to create gates. So a gate is just a solution to a generalized Schrödinger equation that has time dependence. And when I stop, I'm trying to choose this h of t. This is my knobs, my controls, such that the gate, the evolution of the final time is what I want it to be. It's my gate. So you can think of it as a reverse engineering problem. And in general, there's a lot of errors that come in here. The environment fluctuates. There's other qubits around. Maybe the experimentalist who has set up the problem, the device has not calibrated all the parameters correctly, etc. So there's a lot that can go wrong. And what we are, and focusing on superconducting qubits, for example, we can have drifts in frequency. So for example, I might have, my qubit over here, and I might think that it has a frequency, omega q. Frequency means the difference between the two energy levels, and that my control field is, this omega of t. But in reality, there can be errors in both quantities. So the frequency might not be what I think. There might be some stochastic fluctuation, or it might have drifted, and my field might, have some error itself. So it's a quite non-trivial problem. How do I control my system despite having these fluctuations, which I don't know, right? If I knew what they were, I could just put them in my control problem and solve it. So there's a nice formalism set up by my colleague Ed Barnes, which solves this problem of dynamically corrected gates. So the idea is that I can implement a gate despite the error, and in fact, the gate itself can eliminate errors. And there's a nice mathematical formalism that's associated with this work, which is that there exists a natural mapping between the time-dependent Schrödinger equation and curves in Euclidean space, equations called Fresnel-Serret. And that leads us to be able to design curves and incorporate the conditions we want. For example, we want our gate to be insensitive to noise. I can incorporate that into the space curve by fixing some geometric properties. And then from that, I can read off what my pulse should be, what my electromagnetic field should be in order to implement this evolution. And actually, this sounds kind of very formal and mathematical. It is, but we have implemented on hardware. So I want to highlight the work of two people from my group. Vangelis, who wrote, this approach of optimizing space curves and reading of pulses, and Hisham Amer, who took this software and came up with pulses to drive superconducting qubits. And these are qubits that IBM had on the cloud, and they were up to last year allowing people to also do pulse level control. And that's what exactly we did. And what you can see here in the x-axis is error, the error in the frequency and the error in the pulse itself, which we put in by hand to test the pulses. And the y-axis is the fidelity, meaning how close is my gate to what I was intending. And you can see here that, and you want this number, of course, to be close to 1, as close to 1 as possible. And you see that this space curve derived pulse performs really well compared to what IBM does natively. You see it drops here to 70%. So this is the last slide or so. So far, what have we done? We focused on the simulation problem. We said, let's solve something very simple, ground state, and use this variational approach. And in the variational approach, we use pulses. We use pulses to create the gates that enter the variational circuit. But what we could do is just use pulses directly, because in some sense, we're doing something already quite analog. We could go one step further toward this analog idea. And that would take us from the control back to algorithms. So I can set up the same variational problem for finding the ground state of a molecule I'm interested in, which I have mapped onto my quantum device. But then instead of sending in a quantum circuit that I optimize, I just send in electromagnetic pulses. And these electromagnetic pulses carry parameters that I can then vary and kind of go around this feedback loop of minimizing the energy. And we've done some simulations on this. We have some preliminary results on actual devices, but not there yet to show them at this point. But our simulations are promising. What we see is that I can take various molecules. Again, we know how to map these to our device. And then I can take my pulse and kind of chop it up and optimize the different pieces. And then what you see is that you can drop the energy error close to 0 with a small number of time segments of my pulse. What I want to, the point I want to make in the slide is that, for example, for the lithium hydride molecule, if I were to take the gate, the effective evolution that comes out of here on my device, and try to break it up into more digital type gates, I would have an evolution that's longer than the coherence time of the device, meaning than the time that this device stays alive. But instead, if I do this pulse level control, I can do it in 50 nanoseconds. And this, for comparison, is the time it takes to do one gate, one single qubit gate on a superconducting device. So this is something we're exploring further, and we want to understand if this is something that we can scale, at least in the near term. All right, so this takes me to my summary. So quantum processors are not yet to a point that we have quantum computers where we can run arbitrary algorithms. We are sort of going up and down the stack, trying to design better algorithms, but also understanding better the qubits themselves, how they should be controlled, and even having ideas that sort of cross-contaminate each other. I want to acknowledge the people in my group who did the work I talked about. I am very fortunate to have great students and postdocs, and also my senior collaborators. And then finally, let me just show you the other great faculty at Virginia Tech, especially our Virginia Tech Quantum Center, and our space over here, and the nice nature in Blacksburg. So with that, I'll thank you for your attention.
Thank you very much. That was a wonderful talk, lots of exciting ideas, and a great presentation. There were actually a lot of questions that I actually tried to answer some of them while they were talking, but there's still quite a few. Maybe we can take a few of them. The question is, for quantum teleportation, does the teleporting of the quantum state transfer information?
It's a good question. It does not. So I want to make two remarks here. Let me actually try to minimize my screen so I can at least see you. Let's see what's going on. I think I'm having a little bit of trouble here with PowerPoint. Yeah, I don't seem to be able to exit the pointer. It's all right. So first of all, let me point out that what we teleport is a quantum state and not matter, right? The physical system stays where it's at. And the other thing is that even though you teleport the state, the person at the receiving end does not have a way of knowing what state they have until you send them classical information. So we're not violating in any way, things we know from special relativity.
Very nice. There was actually a question. Oh, okay. So there's so many questions coming. Right. Let me try to take an easier one. Can qubits be connected to more than just their neighbors?
Yes, absolutely. So you can have, depending on the physical system, you can have longer interactions. You can have that sort of with qubits staying in place and just the interaction having a longer range. You can also do it by moving around atoms, like I showed you in this reconfigurable arrays. But you can also send down photons. And I sort of alluded to this idea that you can have an atom entangled with a photon when it emits it in the right way or in the right setup. And that photon can then interact with another system that's further located somewhere else, in your device or even further, and then create entanglement that way. Of course, you have to be careful because you don't want to create any type of entanglement willy-nilly and with, any and all qubits. You want this to be a very precise and controlled thing you do.
Okay, so given the time, let me take one last question, and then those who want to stick around later, you can ask your questions that were not answered privately. This question is from somebody we know, Rob Pisarski. Great talk. In a few years, the claim is we'll have hundreds of logical qubits. How would you use such devices, adapt VQE, etc.? Okay,
yeah. Hi, Rob. Yeah, thanks for the question. Rob is a great collaborator of mine. And so the way I envision it, let's say we start having some quantum error correction. It's not going to be an abrupt change, right? We're not suddenly going to have, millions and millions of physical qubits that behave great. We're probably going to have some finite resource in terms of high quality quantum error corrected qubits. The way I think about it is that even if you want to do a so-called more fault tolerant algorithm like phase estimation, state preparation is a big issue. So you need to prepare your state. So I think an interesting way to do it would be to take your physical qubits, which do not have quantum error correction yet, but they are very well performing because we know, we're assuming by assumption they can undergo quantum error correction. So these would be very high fidelity gates. Probably high enough to do some non-trivial steps of adapt VQE. to prepare a state that might not be the exact state you want, but have high enough fidelity, and then transduce that or teleport that, to go back to the teleportation discussion, into error-corrected qubits, so that you don't spend your quantum error-corrected resources, which will be precious, at least in the first years, for doing VQE or state preparation. So I think that's how I imagine that it would play out. And I think it's an interesting direction to work in.
Very nice. Well, Professor Economou, I would like to thank you very much again for your great talk and answering all of these questions. And to everybody for joining us, thanks very much. This will conclude the public part of the talk, but if you want to stay on, you can talk to Professor Economou afterwards privately.